green. Hello, welcome to this webinar on autonomous vehicles. My name is Mike Lambert and I'm chair of the Northeast AD panel of the IMechE. I'd like to welcome Professor Tim Gordon. Tim is Professor of Vehicle Control Engineering at the University of Lincoln. He's also President of the International Association of Vehicle System Dynamics. And with that, Tim, it'd be great for you to start, if you could, please.
Okay, thank you very much, Mike. Yes, so I'm Tim. I've been thinking and talking around vehicle control engineering and in particular autonomous vehicles and more generally automation of vehicles. A couple of quotations on the first slide here. You will ride in a robot car within 5 years. Sergey Brin, one of the Google co-founders. Well, it hasn't kind of happened yet. And second quote from from 2019, there won't be any self-driving cars in my lifetime. So that's Steve Wozniak, Apple co-founder. So what's going on here? Are we really going to be driving in, or are we going to be driven in robot cars in the near future? Well, I'll go through the material, show you the evidence, and you can make up your own minds. And I'm sure we'll have an interesting discussion at the end. Tesla is one of the companies that's heavily involved with promoting self-driving. And you see all the way through promises about what will be coming. Now, I don't think it's fair to be too critical of these promises. So completing a hands-free trip across the US by late 2017. Well, there was a complete hands-free trip across parts of Germany in around about 2010. I forget the exact date. It has been done. It is tricky, and it's very hard to run these things without somebody supervising the system. So much of the so-called self-driving cars these days are simply self-driving control with a heavy level of supervision. Recently, on an autonomy day in April 2019, there's a video, you can look this up. Elon Musk says if you buy a car that does not have the hardware necessary for full self-driving, it's like buying a horse, which I think is a really interesting quote, because horses are actually quite intelligent. Arguably, a horse is a more intelligent form of self-driving vehicle than the current generation. So again, I just like to leave you with that thought. A couple of other quotations, a bit wordy, but look at the highlights. I claim both of these. We have the idea that we will have full self-driving automation. This was in a paper, actually a magazine in the Royal Academy of Engineering, Ingenieur magazine. And me and my co-author, Matthias Lidberg from Chalmers University in Sweden, we figured that it's not really enough. The limitations are at what we call the tactical level in the vehicle, and we'll talk about that later. But we need smart roads. We need smart infrastructure, not just smart cars. And the same message here, that the only way in which we can generate real autonomy is by having the driving environment simplified. Some people will say, well, if we only had self-driving cars on the road, then maybe we could do this. And I think there's some truth in that. Having said that, it is not only the other vehicles for the environment. What about intersections? What about pedestrians, etc., etc., etc.? The visions of autonomy and self-driving have been around for quite a long time. This is going quite a long way back. And you'll notice in some of my slides, I'm going back to the 1950s and perhaps even to the 1930s, because people dreamed about future transportation at those times. So this was a Boy's Life magazine. It was an advertorial, an advertising editorial from June 1956. sponsored by the American Independent Electric Light and Power Companies. So basically selling electricity here. So the highway is electric, and it's also, if you look at it by implication, it is clean. The car is intelligent. We have smart infrastructure in the superhighway. It's safe, convenient, and we would have implied in this picture that it's clean, green, and affordable. Notice there is a steering wheel in the car. People have talked about autonomous driving as being, well, you no longer need a steering wheel in the car. I think this is part of the dream. I don't necessarily think that it is a realistic gambit, as it were. I'll show you a car without a steering wheel in a little while, but I don't think you'll regard it as being what we would call a self-driving car. So this slide comes from 1938, and it highlights a really important part of what makes driving complicated. So this is in a psychology journal, and Gibson and Crooks were postulating about how we plan in driving. So obviously the only thing that really gives us away as being an old paper is the shape of the car. The idea is that the driver is planning a safe field of travel and is doing so by anticipating the movements of, in this case, pedestrians, moving pedestrians. So they will anticipate what the pedestrian is doing and from that map out the safe field of travel. So anticipation of what's going on can be quite important. This next slide is this whole talk will drift between very high level, very general principles, but also some specifics. So since we're talking as engineers, I think we should look at how some engineers, and indeed in this field computer scientists, really look at how to do automated driving, which you can think of as machine driving. How does a machine drive? And in this work of Salvucci and Gray, they use what they call a two-point visual control model. It's very, very simple. Self-driving car algorithms tend to be a little bit more complex, but not massively so. You have a far point, which is a cross, and a near point, which is a dot. And the idea is that your steering angle, or rather the steering angular velocity, is controlled by just a sum of three factors. This is the angle to the near point. This is the rate of change of the angle to the near point, and this is the rate of change of the angle to the far point. And the far point will obviously move around depending on if you're following a vehicle or you're following the edge of the road. Because we don't use the actual angle, we only use the derivative of the angle on the far point, then it doesn't actually matter what you lock onto. You can lock onto the left edge of the lane, the right edge of the lane, or indeed another vehicle. And actually you can simulate realistic or reasonable driving from this very simple equation. This is a more complex picture from a paper that I wrote with colleagues in University of Michigan back in 2009, and this was based on looking at driving data. So this is capturing data from people just driving their cars in a naturalistic way, and we're trying to see, well, what cues are they using? This is all obtained from data on the vehicle, so there's quite a bit of post-processing, but you can see in the left plot on the left edge there is a slightly wobbly lane marker, and on the right there's another slightly wobbly lane marker, and the red dots, it's all very compressed in the vertical direction. These are the parts of the left and right wheels. So actually the driver does not go anywhere close to the edge of the lane, so maybe they're following the center line. However, by looking at some variables that the drivers are sensitive to, we're able to map this into the space of turning rates, or yaw rate. And from that, we can obtain what are the critical yaw rates for staying in the lane within the next 4 seconds. So we compress the time window so that we're looking at the angular rate that is needed to stay within the lanes, not right now, but over the next 4 seconds. And you can see that this is the vehicle variable, this is the yaw rate of the vehicle, and these are the critical values, the upper limit and the lower limit, corresponding to the left and right lanes. So by diving into naturalistic driving data, we can understand better what people are really doing when they're driving, as opposed to what they say they do when they're driving. Here's another picture to show you how complex things can be. This was from another colleague at the University of Michigan, Charles McAdam, and he did some work in a driving simulator where he was able to work out a directional stability boundary, because people will tend to drive their cars so that the vehicle remains stable. This leaves out situations like going into a skid, something like this, but just basically in terms of your speed, how far you look ahead, and also what the driver's own reaction time. So the horizontal axis is says driver transport delay, and that just really means the time that the driver takes to react while steering. So kind of reaction time. And on the vertical is what the preview time is. So, and obviously the speed is factored into that, but these are both times. And it turns out that there's a directional stability boundary that drivers who are less skilled take longer to respond to the vehicle motion and correcting it. So they'll be on this part of the chart. So if you can just about read it, it says novice drivers in the simulator here. But they will also increase their preview time. In other words, they'll look further down the road to see where the vehicle is going. So in that previous picture of Salvucci and Gray, their far point will move further away. So the conclusion from that is driving is actually quite complicated, and even if we only look at steering, it can be quite complicated. I'll read off a list here and just explain what they mean. Stable motion, or let's say reasonable driving, where you don't go out of the lanes and you don't crash into things, involves a number of actions, and this is based on a lot of research. I put in at the bottom there, I put a reference to one of the early, really thorough papers on driving control. I've also put in a picture there which shows a giant bowling ball that's landed on a car. So sometimes we have to react to the unexpected, but most of what we're talking about here is reacting to what is normal. We need open loop actions, which are learnt or pre-programmed, which are things we don't think about. We just do them, and they are learnt. In a computer, they may be pre-programmed as a kind of in this situation we do this, and then we do it, and then we correct it by feedback. We also need preview control to look at forward targets. This is called compensatory, and this second one is called pursuit. We also sometimes need feed-forward control. For example, we may slow down or we may start to steer before we reach a curve, so we're using future information. Basically, we stabilize the vehicle from far point information, the yaw motion of the vehicle, and then we correct the local motion from the near point, again, using that analogy from Salvucci and Gray's paper. That's not to say we don't use a full range of vision in between. We have to predict or anticipate future events, and we have to include other things in our driving. We have to have speed control. Our actions should be smooth. We need to know what the local traffic laws are. We need to know what the conventions are. Just to give you a little bit of a funny story on conventions. I was told, I don't have this from my own experience, but I was told that in some southern states in America, on the winding roads, people will always cut the curve. So if you imagine a two-way traffic, but on a winding country road, the cars on the inside of the curve will cut into the inside. So if imagine you're driving, let's just make it English, we're driving on the left, the turn is to the left, I'm on the left side of the road, I will just cut the corner. The vehicles coming the other way will anticipate that. So they will actually cut the curve on their side because they know everyone coming towards them will also cut the curve. And then you can imagine that in the situation where somebody is from out of town or out of state, they don't follow that rule, then although it's not a real rule, it's something that is expected. So there's also a social dynamic in driving. Now we look at the 3 levels of driving. This is where we get into what I think is the most crucial part. It's so crucial we're going to break it down into smaller levels. But driving really consists of a strategic level, which has got long time constants. It can be minutes, it could be hours, it could be days. What am I going to be doing? Where am I going? Why am I visiting my auntie on that day? It's the strategic level of planning your route. The maneuvering level is the one that's most interesting to us. We're talking about timescales of several seconds, up to about 10 seconds. And that's when we're looking at the traffic, looking at the road, looking at what other people might be doing, and making our immediate plans for what we're going to do to control the vehicle. And then the low level is really the control level. It's the skill level. Things are happening in less than 1 second. We're turning the steering, we're pushing a little bit harder on the brakes, whatever it is. Now, I say this is so important that it's worth breaking this down into various levels. If we start at the bottom, we can think of actuator control, pressing the pedal, turning the steering wheel. Control allocation. To what extent should I steer more? To what extent should I brake more? How do I use the actuators? What's the vehicle doing now? Is it pitching? Is it drifting a little bit? These should be applicable to both the human driver on the top left and the robot driver on the top right. When you break it down into algorithms and actually doing this in detail, you'll find that all of these things have very concrete formulations. We need to do detailed motion planning, the speed, direction, the curvature of the path. We have to evaluate those. Is the path feasible? I'm going all the way up the list. We have to think about situational awareness. What are the main risks here? What's going on? What is that person who's about to pull out from a parking spot? Are they really pulling out? So they're moving a little bit. What are they trying to do? So this is one of the most complex things. It's the situational awareness. We may then have things like enhanced local maps. We're now starting to get into the navigation side of driving. So we're using our Google Maps or whatever it might be. Then at the high level in the strategic part, we're doing planning and scheduling. We're doing some high level mapping. So we're saying, yeah, this route is better than that route because of traffic congestion. And we're doing goal setting. Do I need to drive to work today, or is it okay just to work from home? That kind of thing. And it's that middle section that's the most interesting. The arrows that I've drawn here kind of indicate where I would guess that automated systems, computer systems, robots, if you like, are more capable. So actually most of the arrows potentially go to the right. There's 2 areas where the human driver is clearly going to do better. One is in goal setting. What am I trying to do? Well, I don't think your Alexa is going to tell you what you should be doing today, at least not yet. But the other one is situational awareness. It's about object detection and classification. What is that thing? What's it going to do? Do I need to take account of it? And when we're driving, we're doing this the whole time. And obviously in driving tests, we do that. So that situational awareness and that tactical layer of driving is so important to us. So that really completes the discussion around what is driving. So I think we have hopefully a better picture that it's complex and it's actually made up of various different levels. Broadly speaking, fast ones down the bottom of the list, slower ones at the top of the list. So here's a picture of a self-driving vehicle. It's automated. We probably wouldn't call it intelligent, and we probably won't call it autonomous. Probably some of the audience have already ridden on this. It's at Heathrow Airport, and it takes you to and from the terminal from the parking area on Terminal 5. But what you've got here is that it's essentially fail-safe, it's monitored, and the environment is incredibly simple. In fact, the structure has been built for this purpose alone. So there is no need for tactical driving in this. So the very high level stuff, the goal setting, the scheduling and stuff can be done automatically. And the low level stuff can be done automatically as well. Control of the speed, making sure you don't get too close to the vehicle in front. So that's the low level stuff. So the middle stuff, the tactical level of driving, is almost entirely removed. And that's why we can automate it. And this has been successful. It's been running for more than 10 years and without any I'm sure there's been breakdowns, but there's been no major problems with it. So where did the current interest in self-driving cars come from? It certainly is very easy to pin down, actually. It came from this project, the US DARPA Grand Challenge in 2004 and again in 2005. It's quite interesting. It was a challenge to drive across the Mojave Desert in California, and it basically doesn't involve pedestrians. It's a complicated environment, but being a desert terrain. And these vehicles competed in 2005. It's 150 miles. In the first version, so in 2004, nobody completed the course. The best was Carnegie Mellon University, who completed 7 miles of the 150-mile course. So because of that, it was repeated in 2005. The contestants, as it were given more information. They were able to use map information rather than just using the autonomous information, and that was crucial. So getting better information about the environment and a number of successful completions. There were 5 completions of the 23 finalists. So if you don't know about that and you're interested, you can easily Google that. And they followed it up in 2007 with an urban setting. This is the urban challenge, and you had to complete various tasks in a urban environment. So low speed, but you had to give way to other vehicles, avoid collisions, and so on. There were many failures in that. But this was more focused on the mapping, the localization, the threat detection, and the artificial intelligence. So that continued into what really drove this whole thing was the Google self-driving car. And there's an example there shown of a vehicle with a laser scanner on it, which can look at the environment in 3 dimensions. The laser scanner gives you range and range rate. Sorry, it gives you range to obstacles, but does it on 360. So it not only localizes it, it also tells you pretty much in 3D where objects are. There are multiple scan lines, so you can also see the heights of obstacles. So coming out of the 2005 DARPA Grand Challenge, Google really developed from there. They were able to, you can see that, sorry, I'm just going to, it was 2012 when the world's first self-driving car test. So this is a driving test, as in a human driving test, except that it was the supervised, artificially intelligent Google self-driving car that was doing the work. And they kind of passed the test, but there was nothing formal. But Google did actually cheat a little bit on that. They chose the test route, and they set the limits on the road and the weather conditions, etc. So, for example, roundabouts were excluded from that test. But anyway, they kind of, in quotes, passed the Nevada driving test in 2012. But the challenges are immense, and I think it's fair to say that we're still looking at this kind of development. So in order to look forward, it's actually interesting to look back a little bit more. There's a lot of hype and salesmanship around self-driving, and the previous innovation, if you like, or excitement around self-driving and automation was in the 1990s. So in California, the state of California, with some federal funds and support from the University of California, were developing this demonstration. And I think you can just see some of the interesting points there. One of the interesting points you can't see is that the lateral control of this platoon of vehicles was performed by burying magnets in the road here. And a good friend of mine who was actually working on this project as a graduate student had the job of burying the magnets. So he had to go along the road drilling holes and burying permanent magnets. I hope everyone is still hearing me okay. I just carry on it regardless. So we're going on to another, we can see what the kind of performance that we had from here. So this video is taken at the time. It freezes for the moment when I can keep talking, and then when things start to move, I'll be quiet. But this shows some of the technology of the time.
Scenarios demonstrate the technical feasibility of various types of automated highway technologies and how they will increase safety and decrease traffic congestion.
We'll be showing platoons of vehicles. That's several vehicles spaced closely together. That'll show us some increased capacity options on the highway. We'll be showing a free agent scenario where we have an automated vehicle mixed with manual traffic. That shows how we could incrementally deploy these vehicles in the very near term. We'll also be showing transit vehicles, buses, how they can be automated, along with a number of other features and functions of an automated highway.
For example, the technology the consortium is demonstrating includes adaptive cruise control, which senses vehicles ahead and alters speeds accordingly. This is done through the use of different types of sensors. Collision avoidance, which detects obstacles and other vehicles in the road and safely adjusts the course for a single vehicle or a platoon. Cars can communicate driving information through a combination of sensors and communication signals. And lane-keeping technologies using video cameras or markers that are tracked by magnetic sensors in a vehicle, ensuring lanes are followed precisely. The vehicle can then calculate its exact location in relation to data it rapidly reads.
You will have noticed in this one they talk about some very futuristic concepts, but included was the cruise control. Maybe there wasn't a lot of sound on there, but I don't know if we heard that. But they mentioned about adaptive cruise control. So you've seen in the pictures, at least, that the vehicles are highly intelligent. They're communicating with each other. They're able to do things, but in a very controlled environment. This is basically a demonstration. You might have noticed that there was a regular freeway alongside the test road, and that was just business as normal. They mentioned cruise control, and this really brings me to the next phase in the talk, where we're really thinking about: is it all about revolution or is it about evolution? We hear a lot about, and just in that video and in a lot of the media hype, we hear a lot about the revolution. Soon we won't need to drive a car. Soon we don't need to have a steering wheel. Everybody can be mobile. Your kids can go to school without needing, there'll be a robot chauffeur for them. Wonderful things, possibly, but the reality is not there. So I want to spend a few slides just talking about evolution. Some of this really intense development that happens prompted by things like the DARPA Grand Challenge do lead into real products that are benefiting our lives. So the two are not really one or the other, but largely speaking, the evolution of the motor vehicle is a slow process. And I like to think of it not so much as the evolution of the vehicle, but as the whole system that ties together the vehicle, the driver, the environment, and the technology. So I refer to it as the DVET or the DVET system. And so really, a lot of the development has happened around the vehicle itself. The technology that things like driver assistance systems that will work on the vehicle. The driver themselves don't really evolve, and there's little chance to train and improve the skills of drivers unless they're professional drivers. But the environment has also not really developed. We do hear about smart highways, but that's not what I'm talking about. The environment has nothing like the capability to monitor traffic and interact with it today as we would probably need for full automation. So just going back, we had, going back into the 1960s and 70s, the first electronic control on vehicles. Carburetors were phased out. Electronic control of the engine took over, then anti-lock braking systems, then electronic stability control, cruise control, adaptive cruise control, etc. So these are the really have happened over decades rather than over single years. Adaptive cruise control is interesting because it's the first thing that really interacts with the tactical layer of driving. Vehicle in front of you slows down, your vehicle will automatically slow down. Has limited capability, can't drive you around other vehicles, but it gives you the longitudinal control. There was also lateral control, basically through the development of the actuator level, the electric power assisted steering, so the EPAS, that really came about in the last 20 years, so around about the turn of the millennium. So going from hydraulic to electric, particularly on small cars, but now on most passenger vehicles. And that gives us the possibility of actually turning the steering, of controlling the steering. A system called so, for example, if you're, I'm just thinking here, the EPAS system is already used in automated parking systems. It has to be able to turn the steering. It wasn't developed for that purpose. It was developed just to replace the hydraulic steering assist. But when things become more electronic, they can be more computerized. And steer-by-wire, and also something called lane keeping assistance to keep you in the lane. They have some synergies between them, although you only need an EPAS system to perform this lane keeping assistant, where the vehicle can self-steer within a very limited envelope. Steer-by-wire, it's actually a commercial product on a number of cars, most notably Nissan in their Infinity range. I think it's the Q50 that has a fully steer-by-wire system. So, which means that under normal driving, there is no connection between the steering wheel and the steering system, the mechanism at the front. So there's an actuator there. In between, there is a mechanical system, but it has a clutch that's released. So to meet standards and to maintain safety, if there is ever a fault on the system, the clutch will engage, and then you're able to recover full driving. Then we come back to the commercial development of the systems that we have here, and they go through these different levels. Now, I don't want to talk a lot about them. If you just Google SAE J3016, you can see all of these, but basically we're going to talk about some of them. Level 0 on the left is pure manual, what we've been used to for the last 100 years in driving. And SAE level 5 is full autonomy. The car does not need a steering wheel. Level 1 is driver assistance systems. SAE level 2 is still a driver assistance steering, but maybe all the control actions are done for you. Not just in longitudinal with ACC, not just in lane keeping assist, but both connected together. So the blue ones really are it's on the left, are the ones that are relatively unintelligent, but they're supporting the driver. Level 3 and to the right are ones that are giving us the future, if you like. And here is a demonstration of a level 3 concept. It's maybe not the most interesting video, but if you like the pictures of trucks, it's quite nice. But it does show us something particularly important about automation. And I want you to just notice a few things again in that video. First of all, the environment was very, very simple. The performance of the low-level control systems was very good. The lane keeping was very good, although it was on a relatively simple environment there. They would have been using either differential GPS for that, or they would have been using cameras to look at the lane markings, or a combination of the two. The driver was given 20 seconds to take control of the vehicle. So in level 3, you are able to look away, engage in other tasks, but you must be willing and able to recover control at some point. However, there is a clear picture in my mind, at least, which is that even on level 3, you need a fail-safe. You need to be able to have a plan B if the driver is unable to recover control in time. Also, how do you get 20 seconds of heads-up time on a normal road? If you're driving on the M1, how could you get 20 seconds of driving, headway before you need to do something? In my mind, the only way you can do it is by having a dedicated lane. And this is really the big challenge. Maybe 20 seconds you could argue is too long, but how long do you need? And typically people would say that you need 10 seconds. If you're engaged in another task and then you have to stop that task, move over, see what's happening, regain situational awareness, and then regain control, it's going to take you 10 seconds. So it's a real challenge. Now, there is a video here, but time is running on, so I'm going to skip this. If you want to Google Sartre, this safe road trains for the environment, you can see this. But in the picture at the top, you can see it's a convoy of vehicles where the front vehicle is being driven by the human driver, and then the other vehicles are tagging along behind. It's like they're in an articulated vehicle, except the coupling is purely electronic. The driver in the front vehicle can scan the road, understand what's happening, slow down and stop if necessary. The other vehicles will simply follow suit. So it's a way of simplifying the environment. So I'm going to skip past that. And level 5, I can't show you level 5 because there is no level 5 driving available. Arguably, the Heathrow Airport one could be said to be level 5, but it's not really what we're thinking about. We get out of this dilemma, if you like, by getting out of a rut, by not thinking of mobility as self-driving as being the only thing that's of interest. So in this triangle, on the bottom left, I'm indicating that mobility is the purpose of all of this push towards supporting the driver, level 3, level 4, and maybe level 5 in the distant future. But it's going towards fully automated driving. And it does drive a lot of the technology development. However, the technology development can also be pushed in other directions, such as active safety. And again, if you wanted to have a goal in maybe 10, 20 years, you would say, this will be a car that cannot crash. You can drive it, but it understands the environment well enough that it will just take whatever evasive action is needed to avoid that crash. We're not just trapped in our cars. One of the reasons we enjoy driving, if we enjoy driving, is that it gives us a sense of freedom. We can make the decisions. So avoiding crashes and automated driving are two good things, but we also like driving some of the time. And it's rather harder to define what this really means, but if your car understands what you're trying to do and works with you, that might be what we would call seamless cooperation. And these other texts are really just show you that some of the things that we need to develop to support the automated driving, the bottom left corner, will also be used, can also be used to support the active safety and the driving support. One further comment, it's very important not to mix them up. So if you avoid crashes more because the intelligent stuff on your vehicle is improving at this end, but the inability to drive properly for let's say a rudimentary self-driving car, and if these kind of cancel each other out, is that reasonable? Because we can take away the ineffective mobility on regular roads and we can improve the active safety, then we will cut crashes because of the technology. And my view is that we should be taking active safety as the main thrust, and then the mobility will be improved once we allow, or once we have better environment and we have a better, more predictable environment to drive in. Or we are able to achieve the intelligent vehicle, artificial intelligence that can do as well as people. So I'm going to talk a little bit. I'm aware of the time and we're going to wrap up fairly soon, but this is really around the topic of how can we use all of our smarts, all of our control theory, all our control systems. If we stay in this area here, there's quite a lot that we can do to improve safety. And I'll show you a couple of examples, and maybe it's not just about safety. So this is the one example that I'll give you in the time that's available. It's something called post-impact stability control, and it's at the moment still a concept. You can't buy a car with post-impact stability control running on it. So what's happening is the first event is that there's a vehicle traveling from the left. There's another vehicle approaching it. The blue vehicle brakes. There is a light impact, but that is enough to destabilize the vehicle or cause the driver of the vehicle that's going left to right to veer away. At that point, they can lose stability of the vehicle because of the impact and go off the road and crash with whatever's out there. And so without this post-impact stability control function, you will get knocked off the road at this point. And in fact, it's a surprisingly high number of crashes that have multiple events. An initial event which may be survivable and a second event which may not be survivable in the general sense. I'm not saying that necessarily people are killed, but in other words, you can't recover from that event. With the function, the vehicle would take over, use its very good qualities of controlling the brakes individually. Maybe there is some steering function that can help as well, and then bring the vehicle back to the road. So post-impact stability control. Here's a video which is quite severe, and it shows how a relatively light impact, certainly a survivable impact, is something that leads to something far worse. That plays twice. So what's gone on there? The vehicle is obviously being very badly driven. It's doing a side swipe on another vehicle that's on the entry lane, and that causes it to get into a completely unstable situation, and the driver cannot recover from that. So in general, quite a lot of detailed research has gone into this, so we believe that this is something that can be implemented in the future. So the vehicle, if it has at least some small level of situational awareness, can recover from some initial impact. This is likely to save lives because multi-event crashes or multi-event accidents are something that often lead to severe consequences. And I'm just going to show you a couple of slides which just kind of give you an impression of the analysis. This is these are the available forces and moments that are available on the vehicle. Looking at each wheel individually, we assume here the vehicle takes control of the steering and takes control of the individual wheel braking, which can stabilize the vehicle even while the event's going on. The plots here just show that we were able to get results for a realizable control system, which were very similar to one that we calculated with kind of a brute force computational approach. And then so I'm going to show you one more slide, which just again shows that the algorithms that we're using here, which are highly engineering based, it's real true mechanical engineering stuff. This is quasi-linear optimal control, so this is more or less feasible to run in a control system, but JModelica is an offline optimizer using Modelica language. I'm going to wrap up there and just show you another nice video. So I'm going to go to slide number, I think it's going to be 42. And then there'll be some time for some questions. This is about platooning. You can use other methods to have platoons of vehicles, possibly automated, off-highway. Maybe these ants would represent vehicles that are traveling on maybe in a marshalling yard, so rather like a train. And this is one that I particularly like because it's some work that I'm doing right now. This is in a city called Juzhou in China, and these vehicles are now going into production. Large people carriers. They look like a tram, but they have rubber tyres. Fully electric. And just being commercialised right now. You can see that the local people there are really quite excited about it. It's being developed and built in their home city. Notice the stripes down the road for the cameras to follow. It looks a little bit like that electric highway that we saw right at the beginning. And it has this automated capability. It can be driven. There are actually there are steering wheels at both ends. And this is their animation. This is our simulation of how our controller is a little bit jerky on the replay here. How this can navigate very tight curves. The clue is that every axle on this vehicle steers. There are 6 axles. One can be steered by the driver, or it can be automated, but the other 5 axles will steer accordingly as well. So you can have it maneuverable in the city. So I just want to finish off by saying automation. Yeah, we talked a lot about automation. We haven't actually talked a lot about autonomy. So the bottom left one there we looked at, yeah, it's automated, but it's not autonomous. It's just it's a very light automated rail system. Are we going to go out and buy a self-driving car anytime soon? I don't think so. But that's basically my talk. Thank you for listening.
We have been getting quite a few questions, Tim, so I'll put forward the first question, which is actually a great question, keeping in view that at some stage, or like now, we have a few autonomous vehicles and the same road is used by human drivers. So the question is from Emma, and she's asking, would the problem be easier if human drivers were banned and the only autonomous vehicles allowed?
Absolutely, yes. Although it depends what you want to achieve. We only have a certain amount of roads in our country and in most countries. So the question really is a political one or a societal one. Do we want to use it for automation, or do we want to use it for people to drive where they want to go, when they want to go? But I completely agree with the sentiment that if you mix regular drivers with self-driving vehicles, it becomes too difficult. And so the one on the bottom left of the screen there is perfectly feasible, but there are no other drivers. There are no pedestrians, there are no dogs, there's nothing else to get in the way. So it's a completely predictable environment. So good question, and yes, I think it would be true, but it would also, you would have to develop the infrastructure of our roads. Like, for example, it might be motorways. We'd have to develop that so that we can essentially guarantee that there are no other intrusions into that space and that everything is properly controlled. We actually move away from autonomy to having a traffic control system, as you would have with the Heathrow Airport one. You would have more of a traffic control system, but that's not what people are looking for. They want their, I think the hype is coming from people want everything to be the same, but they just want an autopilot button so that they have a robot chauffeur to take them where they want to go. And I think that concept is not feasible, not for decades to come. It needs major developments in artificial intelligence.
Yeah, so Tim, your comment about the bottom left, the bottom left picture, or shall I say like the bottom right picture as well. It actually links us to another good question raised by Roger, and he's asking, what would you suggest as the difference between the automobile principles you have discussed and a railway? In the end, a smart car and a smart road is a railway.
Yeah, and there's a huge similarity. The main reason for it's good in the context of the bottom right picture. So this ART vehicle can be driven by a human driver. So, for example, if a railway, if there's a bridge is broken or something, the railway cannot function. If there is a congestion or some other traffic accident, this vehicle could still function because it can take a detour. It doesn't have to drive on these dedicated lanes all the time. So I think that's one of the differences. But I would say that automation of railways, which we see a lot of things like the in London, the light railway that goes to Docklands, we have automation for that. Now, the environment for our regular rail system isn't quite as clean as that. I think you need to design the environment straight away. But yeah, I think this mixture of automation and human driven is feasible, and the ART vehicle can show that. You can have this running on its tracks, but where you bring in regular cars into that mix is not clear. It's really tricky. I mean, a lot of the technology is there if we only had the infrastructure, but it's not easy or cheap to just change all of our infrastructure, and we move more towards a centralized robotic system rather than a decentralized, self-driving car that we can interact with.
All right.
And the top right one shows that as well. That was the idea of an automated highway, not an automated individual car. So it's a good question.
Yeah. And Michael is asking that, can we seriously aspire to roads smart enough to support the smart cars within a reasonable time frame?
Oh, that's a wonderful question. I think it depends on the purpose, and I can give you a use case, as people like to say, where the answer would clearly be yes. Supposing that you say that our motorways are not heavily used, particularly in the middle of. They're heavily used during the daytime, but they're not heavily used in the middle of the night. So, what if between the hours of, let's say, midnight and 6 a.m., we decide that one lane of the M1 will become purely for autonomous freight. And so autonomous trucks can then drive on that, and it'll be a highly controlled area. They probably have to have some physical barriers put up to separate that lane. And then during the night time, then we'll be moving all the freight, and we would then see perhaps much, because of tax incentives and so on, and we would see a great reduction in the number of lorries that are on our motorways during the daytime. So it's a kind of a use case where you can think of, yeah, that's possible. We could simplify the infrastructure by putting just perhaps a part-time electrical crash barrier, which comes up during the night time, so you separates that lane and it goes down. I don't know. That's just a rough idea, but dedicating a lane to some special purposes, I think, is possible.
Okay, thanks. And the other question from John is that we talked a lot about electric vehicles and different kind of systems being on the vehicle, and all of that places like an electrical demand on the vehicle. So given the future is electric and battery capacity is constrained, will this be a significant constraint on autonomy?
Oh, again, that's a great question, and it's opening up the whole question of electrification. Just out of interest, this ART, this green road tram, is fully electric, but one of the design concepts here is to reduce the reliance on the infrastructure. So there's no rails, but there's also no overhead cable. In the video, it does actually show it coming into a station, and the pantograph, the pantograph on top will then go up and be charging the batteries partially while it's stopped at the station. So it will be able to make its city trips by occasionally topping up the charge and then doing a full recharge at the end of the trip. I have to say I don't know the answer to this. However, you can see from the top right picture that you don't need electrification for automation. Those platoons are done, obviously a lot of electronics in there, but no electric vehicles.
Another question from David. He's saying, you have talked a lot about how humans drive. Playing devil's advocate, our track record as humans is not great. Driver main cause of accidents. Should we aim autonomous driving at how cars should drive, not how we as humans drive?
Okay, that's a brilliant question, and I agree with the devil's advocate bit. Basically, you can, if you drive for a lifetime, you drive for 50 years, you may be involved in one or two accidents typically in that time. When you compare with autonomous vehicles, it's easy to prove that autonomous vehicles are a little bit safer. However, those autonomous vehicles are level 2 vehicles. They have one or more supervisors whose job it is to keep that vehicle safe. And they will take over regularly to avoid any difficult conflicts. So there really is no data on how well a computer can take over from a human in doing the driving. So while I agree, when you look at some of human performance in driving, it's terrible. I mean, we drive down the road and we say, look at that person, they're really such a bad driver. However, we seem to be, evolution has taught us something. It's how to avoid very serious crashes, unless we are, in a very unusual set of circumstances, or whether we're drunk driving or something like that. So actually, humans are much better at avoiding crashes than you would expect. And I did some calculations based on published data. And if I remember correctly, you would have to be driving for 100 or more lifetimes before you could expect, on average, to be involved in a crash where there's a fatality. And that's not necessarily your fatal crash. It's somebody else in the crash who was killed. So we actually do a pretty good job. There is no proof that artificial intelligence can deal with that middle layer of driving and achieve the same level of safety. Arguably, if somebody said, do you want your child to be driven to the school in a robot taxi, you might have that thought in your mind. How safe is it really with full autonomy? But a great question.
Yeah, and another question from John, which kind of follows on from the question of removing human drivers from the mix. Do we have any idea how we can ensure different manufacturers of automotive systems will interact and ensuring they interact correctly? For example, Nissan vehicles and Fords, or different ages of automotive vehicles.
Well, I have to say I'm not completely knowledgeable about this, but I do know the way automation is being developed in a small number of companies. I'm not aware of their development plans being strongly influenced by legislation, which is the only way that you can do this. So there is no big cooperative partnership of companies in developing automation. There are individual corporations, don't get me wrong, but broadly speaking, it's all being done on a commercial basis, not on a legal or government, mandated. So And I think it is important. You need, if you're going to have a partially automated vehicle, which is realistically what's going to happen, you need to have a common interface so that when you get into it, you know what to do. You know what various interfaces mean. And at the moment, I don't see a lot of commonality in that area. It will be needed in the future if automation becomes more common. So another great question.
Okay, yeah, I think we are coming a bit over time. I'll maybe just take a couple of more questions. A question from Rob, and that is, as technology increases, driver ability decreases. Do you think drivers will struggle going back to driving old cars?
I think they may have to relearn. It's possible. Yeah, it's certainly possible. I mean, one example of that is that, particularly in North America, very few people drive with manual gearbox. So, yeah, so they never learn. So to drive with a manual gearbox is really quite challenging if you never had the experience. Of course, you can pick it up pretty quickly. It's just a skill like any other skill. But the idea of, in theory, I suppose that will emerge when you no longer have to evaluate threats and risks on the road. I guess you go back to driving school, but it's a really great question.
Yeah. Okay. Maybe just one last question. What are the legal and moral implications resulting from automated cars and possible accidents? This question is from Malik.
Sorry, I didn't completely understand the question.
It's asking that what are the legal and moral implications resulting from automated cars and any possible accidents involving automated cars.
Mm-hmm. Okay, well that is a very, very important area. It's normally expressed in terms of a fully autonomous vehicle, where the artificial intelligence in the vehicle is making life and death decisions. So the ethical and moral and legal issues associated with that. To me, this is largely a futuristic question. There may be some cases where the vehicle has to make some kind of decision, but realistically, with the current generation, it is not an issue. It will come from the algorithms that have been pre-programmed and have been approved by the authorities. So what happens, happens. Just like if something goes wrong in a mechanical system, what happens, happens. There is no judgment on, do I save a life or do I do this? But there will be some algorithms in there. For example, if the self-driving car has to, and this is probably your level 3 vehicle, if the driver does not take over, it's unlikely that it would do an emergency lane change. That will be in the software. It's much more likely it will do full braking, and if there is a frontal collision, then what happens, happens. But by making a more active decision without the driver's input to change lanes, that could lead to a head-on collision and could cause more damage. And under those conditions, I think the algorithm would have been unacceptable. And I don't think our companies would do that. I think there's also interest in that when you look at the active collision avoidance systems, like the one I explained for the post-impact. And I think what you have to do is give the vehicle minimal powers in some sense to correct the worst cases rather than making active decisions to do something completely different. It is difficult. I think it's a real challenge for developers of collision avoidance algorithms, but I don't really share the concern others have with the ethical and moral aspects of, do I make a decision that's going to kill these 3 people or should I kill this one person? I don't think that the artificial intelligence has the situation awareness these days to make that decision. And it may be that they never do.
Okay. Thanks a lot, Tim, for answering these questions. I guess there are a few more, but we are right over this hour. So thanks a lot.
We are indeed.
Yeah.
Okay. Well, and thanks I'd just like to thank everybody for their attention, and it's already good. It's always good to hear these questions. So thank you.
And I would ask Mike to give the closing remarks.
Yes, thanks, Tim. Hopefully you can hear me as all the outsiders. I don't know what they're doing, grinding stones or drilling or something. But thanks, Tim, for a great lecture. I really thought it was really, really good. And thanks to the audience, too, for lots and lots of engagements. We have lots of questions, too. And I think that those can be answered via responses and emails in something that will be sent out, Emma, yeah?
Yes, that's fine.
Okay, that's great. So, thanks everyone. That's the end of the webinar. And thanks again, Tim. We managed it on the third attempt. Pandemics or not, we got it done. Thanks very much.
Thanks, Mike.